All right, so these are our notes on ionic compounds. So ionic compounds, some of their properties are that they're electrolytes, which means they conduct electricity when they're dissolved in water, and this is because of the ions. So we talked earlier about cations and anions, specifically when we were talking about isotopes, and these cations and anions is when we look at the amount of electrons and protons in that balance. So a cation has more protons and electrons, has a positive charge. Anions have more electrons and protons, and they have a negative charge. And so because we have these charges, they conduct electricity. They also have electrostatic attractions from the positive and the negative ions. And so what that just means is it allows them to have strong bonds called a crystal lattice. So they have a very strong structure in that bonding, and it makes them hard, meaning that they have a composition where it's hard to break the bonds. So they have strong bonds, which requires lots of energy to break, and this causes high melting and boiling points. So in order to break these bonds, we have to add heat if we wanted to break them into their individual elements. They have crystal structures, and those depend on the elements being bonded as far as the shape of that crystal structure, and they must combine to form neutral compounds. So we can't have a positive or negative charge. These have to balance. So these look a little bit different. Rather than sharing electrons, they either give away electrons or they take electrons from another element. So in this example, we have calcium and bromine is a combination of one calcium ion. This is our cation, and it has a positive 2 charge. And then we have 2 bromine. Bromine has a negative charge, 1 negative, 2 positive. So if we have 2 of these, that'll give us 2 negative. This gives us 2 positive, that equals 0. All right, so how do we draw these ionic compounds? So we're going to first draw their Lewis structures and then figure this out. So I'm just going to grab a pen down here. All right, so we're going to write magnesium, Mg. And if we look at our periodic table, magnesium has 2 valence electrons. And then we have chlorine. Chlorine has 7. So it takes energy to give away or take electrons. And what we're trying to do is fill these valence shells. So chlorine only needs 1 valence electron to fill its shell. Magnesium would need 6. And so it's easier for magnesium to give an electron to chlorine than it is for chlorine to give 6 electrons to magnesium. Now, that gets rid of 1, but magnesium has another valence electron, and it wants to get rid of it because the shell below it is full, and we want full shells. So we're going to add another chlorine in here. Again, 7 valence electrons. And so it's going to give an electron to chlorine to fill its shell. And so to write this, we would write MgCl2. Okay. We can also write it with the charge. So if we think if magnesium is going to give away 2 electrons, it means it's going to be more positive. It's giving away 2, so this would be Mg2 plus, because it has 2 more protons and electrons. And then our chlorine is getting a little extra electrons, so it'd be negative, and it's still that 2 because there's 2 of them. If we look at our charges, 2 negative, 2 positive, that's neutral. All right, calcium with oxygen. Oxygen has 6 valence electrons. And if we look at our periodic table, calcium has 2. So this one's just going to be 1 and 1. Calcium is going to donate its 2 valence electrons to oxygen. So now they're both full. So this would be CaO. If we wrote it with charges, this would be Ca2 plus O2 minus. Okay, and those charges work themselves out. All right, I want you to pause the video and I want you to try number 3 and 4 on your own. And then when you're done, you can play the video and I'll walk through them with you. All right, so cesium has 1 valence electron, and iodine has 7 valence electrons. Sorry, they're starting to look like lines on here. We're going to take and we're going to give a valence electron to iodine, so this would be CSI. I'm not going to do the charges on these ones. You certainly can if you want to. And then we have magnesium and phosphorus. Phosphorus has 5 valence electrons, and magnesium has 2. All right, so magnesium is going to give this phosphorus 2 valence electrons. However, phosphorus still needs 1 more, so let's get another magnesium. All right, phosphorus is full, but magnesium still has 1 left. So let's get another phosphorus. All right, magnesium will give that to phosphorus, but still needs 2 more. So another magnesium with 2. We'll do it down here. And so now 2, 4, 6, 8, 2, 4, 6, 8. So this would be Mg3P2. So this one's a little more challenging. We really have to think. We got to make sure that they're all full. So if they're giving away electrons, they can't have any left because their shell below it is full, and we want full valence shells. And the one that's taking has to be full. So we have to think of the combination of how many of each we need to fill all of those shells so that we have a neutral atom. All right. So there is this really nice method to the periodic table that shows us a pattern, and you can feel free to write this on your colored periodic table if you'd like, but all of the elements that are in this column are 1+. They are going to give away 1 valence electron. Now, we're not going to worry about hydrogen or helium. And the reason that we're not going to worry about them is because they only fill their first shell. This only has 1 electron. This only has 2 electrons. They really don't like to give away their electrons. This one has a full shell. It's a noble gas. This one, an element can't really give away its only electron. And so these elements are involved in covalent bonds where they're sharing electrons with another element. They don't participate in ionic bonding. Okay. This column is 2+. So this column, these are all going to give away those 2 valence electrons. We're going to skip this area for right now. We'll come back to it. This is our transition metals, and they have their own special rules that we'll learn a little bit here. Of course, again, always different conditions here. This column is 3+. This one's a little different. This one is 4+, 4-. It is right in the middle, so it can either give away 4 or take 4 depending on what it's bonding with. This one is 3-, 2-, and 1-, and we know that these are noble gases, and they already have full valence shells. They are not going to bond. All right. Well, before we were trying to combine and figure out how many of each we need, there's really a shortcut to figure this out. We're going to do an example with sodium and sulfur. So we first write down the charge. This charge is also called the oxidation number of each ion. So we know that sodium, looking back at that periodic table we just looked at, that this is a+. It's in that first column. And sulfur is a 2-. So we write the 2 symbols side by side with the cation first. How I always think about this is that cation, it's positive to negative. This one's always going to be further left on the periodic table. This one's going to be further on the right. So it's kind of like writing left to right, if that helps. Okay, then we're going to make a neutral compound by making sure that the charges are equal. If the charges don't balance out, then we do a switcheroo, or some people call this the crisscross method of only the numbers and reduce the numbers to the lowest multiple. So what we're going to look at first is this. Does that balance out? Okay, it doesn't balance out, so we know that we have to have more than at least one of these elements in order to get a neutral compound. So in the crisscross method, what we're going to do is we're going to crisscross. So the symbol from our sodium, we know that this really means 1 plus. So that means this subscript is 1 as well, but we don't write the 1. And then we're going to take the 2 here from the sulfur. Whoop, sorry about that. Goodness. We're going to take that 2 from our sulfur, and we're going to crisscross it over and put it down here for the sodium. Okay, really quick, easy way to figure it out without having to draw Lewis dot and moving around arrows every single time to figure out formulas. All right, so you're going to try some of these. Or I'm going to show you a couple examples and then you're going to try some. So we have magnesium bonded with oxygen. So our magnesium is a 2 plus. Our oxygen is a 2 minus. Their charges balance out, so it's just MgO. Mg with F, Mg is a 2 plus, F is a negative, so we're going to do the crisscross method here, crisscross, and that's how we find those. Okay, now I want to talk about the lowest common, if we had to factor these. So let's say I did a calculating and for whatever reason I got, Mg2 and F4, okay, which is just a multiple of this. If we can see they're divisible by the same number, we're going to divide them to get the lowest common factor. So these are both divisible by 2, and that will give me our MgF2. And that's what they meant on that first slide with the directions is dividing these by a common factor so that they're at their lowest multiple. All right, so I want you to go ahead and pause your video and try these two. We have aluminum and oxygen and strontium and chlorine, and then you can press play and I'll walk through these with you. All right, so we have aluminum. If I look on the periodic table, that has a charge of 3 plus. Oxygen is a 2 minus. So with our crisscross method, Al is going to be a 2 and O is going to be a 3. And they're not divisible by anything for a common factor. So that's balanced. All right, then we have strontium and chlorine. Chlorine is a minus. Strontium is a 2 plus. So this would be SR1 Cl2. All right, this is the end of the ionic bonding video part 1, and you'll have to play. There's a part 2 that will take you through the next page of your notes. Thanks.